right, so review of week 4 stuff, right? Let's start off with alkenes and heat of hydrogenation. I hope the quality is decent. Okay, cool. All right, number 1 rule, comparing alkene number, right? So lower alkenes essentially means lower heat of hydrogenation. So this one, we're gonna say number of alkenes is proportional to heat of hydrogenation. That is the number 1 rule for the first thing. So if I have 2 alkenes versus 3 is obviously the higher one, higher heat of hydrogenation, because you have more alkenes, meaning more energy whenever you basically hydrogenate them. It's pretty much the simple rule of it, so there's nothing much else. Yeah, that's the direct relationship. So say in the case now that you have ruled out 2 versus 3, that's fine. And now you have the case of a 2 alkene containing compound with 2 alkene, right? So in this case, I'm gonna remove that. The second rule is stability of the alkenes that are related, right? So this stability, focus on the stability, is inverse, let's say, has an inverse relationship with the heat of hydrogenation. And I'm just using the triangle figure as the heat symbol just for convenience. But yeah, that would be a thing you should familiarize yourself with, because that is the symbol you'll see. So inverse relationship with heat of hydrogenation. So as stability goes up, so you increase stability, I will decrease the heat of hydrogenation. Example, if I have in a figure with, we'll say this is 1, this guy has 2 alkenes that are conjugated versus, I want to say that's C, well, okay, good. 2 alkenes that are isolated. Obviously, we know based off of this stability factor, we know that conjugated have the highest stability, then isolated, then cumulated. So if I was to think inverse, as I'm going downwards, my heat of hydrogenation is increasing, if that makes sense. So stability would go up from cumulated to isolated to conjugated, but my heat of hydrogenation would decrease going that way. Now, if I was looking at it from a stability going down, if I was to decrease stability going from conjugated, isolated to cumulated, your heat of hydrogenation would actually increase. So those are the relationships whenever you put them in tandem. But back to the example, say I had 2 isolated alkenes. We'll just say these guys. Essentially, if I was to compare them, first rule, 2 alkenes, okay, you're good. You're able to compare these. Second rule, so we'll do first rule is done. First rule here, done. Second, determine stability in relationship to heat of hydrogenation. Conjugated is the most stable, so you're going to have the least heat of hydrogenation, or the lesser in this case. Isolated has more, less stability. Therefore, it has more heat of hydrogenation. And here, just for the sake of it, more stability. I am sorry if this is not super organized, but hopefully that makes sense. That's the gist of it. Memorize these 2 rules. The alkene number and the heat of hydrogenation is a direct relationship. The stability and the heat of hydrogenation is an inverse relationship. If you understand that, you're good, you're chilling. And remember, you have to satisfy the first rule. For the first rule, primarily, if you have 2 alkenes, you can compare them with a compound that has 2 alkenes. You cannot compare compounds with 2 different numbers of alkenes first, because your first rule has to be applied. That has to be applied. So that's the essentials for heat hydrogenation alkenes. Just for timestamps, this is until 5:11. Kinetic and thermodynamic reactions, right? And on the side here, if you see me zoning out on the side, it's because I have my laptop. But example, right? So we'll start off just with a very simple one. And I'm just gonna use the group work stuff because I think taking it step by step with an actual problem is better. First things first, 0 degrees or like -10, you might see -10 on the exam, is essentially low temp, which correlates, let me just show you this, it says, to kinetic. So this was kinetic. High temps could be anywhere from 40 to say 100 degrees. That would be, I've seen 100 degrees on the exams before. High temp, which refers to thermodynamic. Okay, now, another thing that's really simple, a general rule is that a kinetic will always make the 1,2 adduct. Adduct being the resulting product, that's just the name of it, but you've done it 1,2. So meaning, like if I was to refer back to this guy, okay, well actually we'll go back to that, never mind, because I want to talk about symmetry first. But that's the general rule. The kinetic product will always make the 1,2 adduct. Thermo is different. Thermo can make either, the 1,2 or the 1,4. The key for thermo, the thing I would want you guys to take here is most stable alkene equals your priority. It doesn't matter if you think the most stable alkene will be a 1,4 because thermodynamic is usually 1,4. That's not the case. Don't ever think that. If you're gonna think about thermodynamic versus kinetic will always make your 1,2. Thermo can make either. So think thermo can make either, but the key behind it is that thermo makes the most stable alkene. Always just look at that. Most stable alkene, that'll make your life much easier, and you don't confuse yourself whenever you're like, oh, 1,4, 1,2, because on the exam, she might have questions where she'll ask, oh, is the thermodynamic product the 1,2 or the 1,4 adduct? Okay, well then from there, beforehand, you would have to have seen which one of the 1,2 or the 1,4 has the most stable alkene, then you decide. Yeah, and keep in mind, the thermodynamic product can be the same as the kinetic. It can be the same as the kinetic. And what I mean by that is, if the most stable alkene is in the compound, that's the 1,2 addition, that is the same thing, obviously, as the kinetic. The kinetic product is always the 1,2. If, in the case that the most stable alkene is the 1,2 product, then the thermo and the kinetic are the same. But for now, just think of it as thermo, most stable alkene, and then whether or not they're the same as the kinetic really doesn't matter too much. That's just a rule you don't get confused. So it's like, if you see something that's kind of like abnormal, like, oh crap, the thermo is the same thing as the kinetic, am I wrong? No, that's definitely possible. That's a thing that can happen. So, bear that in mind, that's okay. Back to here. So we're gonna take 2 examples and we're gonna walk through both. One thing I will note, please pay attention to arrows and number your carbons whenever you start. So first things first rule whenever you're walking through these guys, symmetry, right? If this compound is symmetric, and I say this because you're supposed to determine at the ends of the conjugated regions only, I'm gonna keep these guys in big dots because these are the only carbons that I care about whenever I'm adding hydrogens. Hydrogens, keep this in mind, the hydrogens of, let's say, HBr, HCl, anything that resembles the acidic form or the proton. This is essentially because you're doing a proton transfer for the first step, right? Anything that resembles this kind of basis, the hydrogens are always going to go to basically carbon 1. So that's why numbering your carbons is the most important, but don't confuse yourself. If it's symmetric, 1 and 4, whichever one you number, they're the exact same. It doesn't matter. So I can number it from the left to right. I could also number it from here. That's why sometimes Dr. Bliss has like interchangeable numbers. They're the same because they're both symmetric. And what I mean by symmetric is when you're looking at carbons 1 and 4, 1 and 4 carbons, I'm going to note this, 1 and 4 carbons are the only ones you look at. 2 and 3, they just make the carbocations, right? So they just deal with, okay, they don't make the carbocations, but they deal with whatever happens after the first. So they're not super important. I'm just going to keep this kind of like, I'm going to keep that erased because I don't want to confuse you. 1 and 4, always the first thing you're going to look at is carbons 1 and 4. 1 and 4, 1 and 4. Now, determining carbon number 1, determine carbon 1 is based on less substituted side. Less substituted meaning less substituted with carbons, with carbon branches, or anything that's non-hydrogen. If it's easier for you to think, this also means more hydrogens. If it's easier for you to think. And this is based off Markov-Nikov's. Markov-Nikov rule. So essentially, I'm going to look at the less, oh, did that pause my, oh crap. Okay, hopefully that's fine. Hopefully nothing crazy happened. But okay, basically look at the ends of the regions. So 1 and 4, the end of the conjugated regions are the end carbons. That's what she means. So just look at the end carbons of the alkenes, carbons 1 and 4. Determine less substituted, right? Less substituted. Because this is a symmetric compound, both sides are the same substitution. You have 1, 2, tri-substituted for this guy. Tri-substituted. This one, 1, 2, 3. Tri-substituted. So they're both tri. So it doesn't really matter. They're both tri-substituted. Now, I don't mean alkene after I've done the reaction product and all that. I'm just looking at where I want to number my carbons first. That's the first step. Step 2, okay? Once you've numbered your carbons, determine what 10 degrees Celsius or 40 degrees Celsius means, right? You know that this is kinetic, meaning I'm going to do the 1,2 addition. This is going to be the thermal because it's a higher temperature. That could be either 1,2 or 1,4, but the key, remember, most stable alkene. Perfect. Okay. Now let's say step 3. So you are given this guy, which is here, here, here. Boom. We're going to give you guys HCl, and we're going to do a thermodynamic because the kinetic products I feel like you guys would understand pretty easily, and it's not super tough, but I could do it in case. So we've determined this is thermo because it's a 40 degree, and we have HCl. You know, those are kind of like a landmark of it, so it's fine. Hopefully that's gonna be seen. Okay, good. Now, I'm just gonna number using, remember, these carbons are my focus. 1, 2, 3, 4. First things first. Now, whenever I'm doing this guy, it's just a very simple proton transfer, and these arrows are extremely important. Remember, it's just you're just gonna use carbon 1 once you've identified 1, 2, 3, 4. Just use carbon 1. That's all you gotta use. You're gonna make an arrow to hydrogen, which will break this bond in between hydrogen and Cl. These 2 arrows are extremely important. You have to draw these for the sake of the exam. I will tell you right now, these are important. This bond between the H and the Cl, this bond right here, is extremely important. That guy must be drawn. That must be broken. So you have to draw this arrow coming out of it. I'm just gonna erase this so it's cool. Okay, now we've added a hydrogen to this side, to carbon 1, meaning that I am left with an unfulfilled carbon 2. That's kind of what I was drawing to at the beginning. Carbon 2 gets affected, right? So the effect of the first step of the proton transfer, I've added the hydrogen, carbocation is now on carbon 2. So I'm just gonna number my carbons again. Oh, I'm sorry, this should be 4. 4, okay, cool. 1, 2, 3, 4, boom. Now this is, what's it called? What would be a kinetic product, correct? So regardless for thermodynamic, you have to make both, right? Because you have to determine whether the 1,2 or the 1,4 is the more substituted. So in the case of this, it will actually tell me my kinetic product would look like anyway. So that'll be fine. So we're gonna go ahead and add the Cl now to this guy, to the carbocation. Remember, he only adds to the carbocation because he's unfulfilled and he needs a spot. So we have here, here, boom, boom. Oh, sorry, that might be a little bit tough to see, but hopefully it's legible. That's the double bond. And then Cl's here. Okay, now analyze the stability of the alkene. Basically, by stability, substitution, right? The more stable is going to be tetra. The less stable is going to be mono. And then obviously tetra, then tri, then disubstituted. Now, this is going to be tetra. Look at your substituent carbons. 1, 2, 3. Remember, when you're looking at substitution of the alkene, only look at substituents that are carbons, not hydrogens. Hydrogens don't count as substituents whenever you're looking at stability and substitution. So this hydrogen that's here, I'm not counting him at all. Don't count him. These three, only these three sections. This makes this alkene tri-substituted, which is pretty high in stability. And then that is the 1,2 adduct. 1,2 adduct. Because I simply added the hydrogen to 1, which will always happen, and then 2 got the chlorine, which might not happen. That's where the thermodynamic comes in. Now, if I'm going to do the second product, and this is where the resonance comes in. Now, just begin again with the same compound so you do not confuse yourself. But remember now you have to do resonance because your alkene has to move. You can't not move this alkene and then create a different product. That doesn't make sense. You're not going to make a different stability alkene. So, HCl again, and we're going to do the 40 degree. It's still a thermo, but I've just done the 1,2 adduct, and now I'm doing the 1,4 in order to determine which one is more stable, therefore which one is my thermo. So I'm going to highlight these. I'm going to keep my numbering the same. Boom. And I'm going to attack with 1 always. 1 always grabs the hydrogen. This bond between H and Cl breaks. Always needs to draw that. Now, when you draw this, we have the same thing as you saw up here, but I just want to do this for the sake of explanation. There's going to be a cation because he's unfulfilled now, but this carbon 1 was fulfilled with a hydrogen. 2 got nothing, but he might get something later. Now you have your resonance. What this can happen. Remember, also another reason why you'd never add your hydrogens to 2 or 3. If you do so, you can't actually resonate because your carbocation becomes at the end. And so, say I had a carbocation here, this alkene cannot reach here. You can't cross 2 bonds, 1, 2, to get to a carbocation. So that's also why you only add hydrogen to carbon 1 only at the very beginning of these reactions. Now, when you do this, you're going to resonate just kind of like how you did in Orgo 1. You just resonate to the adjacent bond. And you're going to have to move your carbocation. Once you move the alkene, the carbocation moves with it. That's an important rule that you need to just kind of like refresh on. And we're going to keep on going. So now we've created a new alkene, which is the purpose whenever you're finding the thermodynamic product, because you have to make 2 different alkenes, remember? And you need to close these brackets because this is the only ones that do resonance. Now you've moved this here. This becomes satisfied. So 1, 2, 3, 4. 2 is satisfied. 4 has become unsatisfied, right? So 3 got satisfied again by the creation of the 2,3 alkene. Now 4 is left with the carbocation, right? Then Cl, he takes his chance. Whenever he goes for the carbocation, he can attack and he can basically add to it. And then you've created a different product that can become what you think could be the thermodynamic. Now, this is the 1,4 addition, right? 1,4, 4 coming from 4. Okay, actually another way of saying this is 1 means hydrogen attached to it, right? In the 2 or 4, 2 refers to where the chlorine went, 4 refers to where the chlorine went, just for the sake of understanding that again. Now you have the 1,4 adduct, the 1,2 adduct. Now, the 1,4 adduct is not automatically my thermodynamic product. That's why I don't want you guys to think, oh, thermo is 1,4. That's not true. 1,4 here, if you look at the substitution, you've got 1 and then 2. 2 carbon branches, right? I only have 2 of them, making this di-substituted, making this guy less substituted than the 1,2. Thus, because he is less substituted, the 1,2 adduct, which is tri-substituted, is the thermodynamic product. He is our thermal product. Now, in the case of the exam, sometimes whenever you see major and minor, the major product for a thermodynamic reaction is the more stable alkene, right? So the major is the more stable alkene, or I'm sorry, the more substituted. The stability and the substitution go hand in hand, so that's okay. That's a direct relationship, but I don't want you guys to confuse this with this stuff. Just don't worry about that. Minor is the less substituted. So this guy, in the case of this problem, the major one is actually the 1,2, which is this dude, because he's tri-substituted. The minor is the 1,4, which is this dude, because he's di-substituted. He's less substituted. So that's how you would do the resonance as well. So the resonance, you just follow the simple way of trying to do a kinetic one, but the one step that's important is that the alkene moves towards the carbocation. Remember, your alkenes move towards the direction of the carbocation. That's the important part of it. So hopefully that makes sense. And remember, thermodynamic, the biggest thing, most stable alkene, which refers to most substituted alkene. That's the priority. Then you determine which of those, of the 1,4 of the 1,2 is that. Remember here, the kinetic product, which actually is this guy, if you think 1,2, 1,2, 1,2, the kinetic product and the thermodynamic product are actually the same. So if I was to give you this dude, and is that still seeable? No, it's not. Okay. Now he's seeable. Boom, boom, boom. If I was to give you this under 0 degrees, kinetic, I'm going to do 1, 2 always, 1, 2 always. We're going to label my carbon. Sorry, I did not mean to circle this guy. This guy, remember? 2. Nope. Don't worry about 2. 1, 2, 3, 4. 1. Make sure you draw this bond. This guy, you have to attach it to it. Boom. H. Carbocation, because he's unfulfilled. 2 is unfulfilled. And then we're going to have Cl attack him. And then you have no resonance in this one. Remember, the kinetic products have no resonance because you have not moved the alkene. The alkene has not moved. There's no need for resonance at that point. And this is your kinetic product, which matches up to here. These guys are the exact same thing. Kinetic, 1, 2. And it's because 1 and 2, 3, oh. No, I missed a bond. I apologize. I missed a bond. I'm sorry. Please do not kill me for that. Hopefully that's not confusing. Sorry if that was confusing. Okay, cool. 1, 2, 1, 2. Remember, 1 where the hydrogen goes, 2 or 4 where the chlorine goes. Cool. So the kinetic and the thermodynamic product for this one is the same. This problem I kind of did on purpose for the sake of kind of showing you how it doesn't matter what thermo means in terms of 1, 2, or 1, 4. It just simply means most substituted alkene, which then can tell you if it's the 1, 2, or 1, 4. So timestamp for this is the end of its 21:15. Okay, cool. All right, so we're gonna move on. Yeah, sorry if this is gonna be a lot of rambling, but I did want to go over orbital theory, what you need to know about that, because I saw that on the Friday worksheet. Okay, you see these balloon-looking things? So orbitals are essentially these balloons. They look like double-headed balloon, not double-headed, 2 balloons stacked on top of each other. And sometimes you'll see them opposite side, this, and that. If I'm going to be completely transparent with you, you don't need to know what this means. You don't need to know how they overlap. You don't need to know that 3-dimensional trigonometry, confusion. The key is orbitals are basically, say you have, actually, let's go with an example because that'll be easier to explain. We have this compound, correct? You have 2 pi bonds, which amounts to 4 pi electrons. And why? That's because each pi bond, 1 pi bond, has 2 pi electrons. So therefore 2 times 2 equals 4. Now, your number of pi electrons is equal to your number of orbitals. Orbitals being these ugly looking balloons, or also seen as these little stepping stones. So if we know this, say for this compound, what his basic, his orbital diagram would look like is, we're gonna bring him down actually, because I don't want to confuse. He's essentially, we have 2 pi bonds, meaning 4 pi electrons. Therefore, we have 4 orbitals. Now, remember, you have a ground state and an excited state. These are important. Excited, ground state means I have done nothing to these pi electrons. Nothing has happened, nothing. Excited means I have added photochemical energy to them. And that's fancy for, I basically charged the electrons. That's all it means, okay? So I charge the electrons. And that means I move one electron upwards an orbital. Now, you might think like, bro, what does that even mean? Give me 2 seconds, I'll explain that. So like we said, 2 pi bonds, 2 electrons per pi bond, 4 total pi electrons. Then the direct relationship, 4 pi electrons means 4 orbitals. If I have 6 pi electrons, that means 6 orbitals. Cool. Orbitals being these balloon things, but they're represented by these stepping stones whenever you're doing the diagram. 1, 2, 3, 4. 1, 2, 3, 4. 4 orbitals for each. And then we have the levels. Obviously, these levels are just kind of like this weird Greek symbol, so it's not that deep, but boom. Okay, now this kind of goes back to chemistry. Whenever you're filling up bonds, each of the orbitals can take 2 electrons, correct? Now, when you're going up on the ground state is different because you didn't have one of the electrons of your higher level move up, so it just kind of stays the same. And essentially, you're going to start from the bottom, and you're going to fill your orbitals with 2. So in the ground state, fill up each orbital with however many, so it has 2 electrons each, right? Fill them up until you can't. I have 4 electrons to work with. I'm going to put 2 in the first, opposite arrows, 2 in the second. I'm left with 0. That's it. Ground state is done. I don't have any electrons remaining. Now, this brings up the idea of HOMO and LUMO. HOMO is highest occupied, referencing you have electrons in it, you have electrons in the orbital. LUMO is lowest unoccupied. The key is unoccupied for this guy, meaning you have 0 electrons. So that's why on the Friday worksheet, basically LUMO is always 0. So it's essentially always 0, always, because you don't have anything. It's the lowest unoccupied. Now, highest occupied for ground is essentially going to be the highest level that has electrons. So that's why 3 isn't. 3 doesn't have any electrons. Even though it's higher, it has no electrons, therefore it's not the HOMO. The highest occupied, if I go down from 4 to 3 to 2, 2 has electrons and has 2 of them. It doesn't matter how many there are in here, as long as there's one, at least one electron, as long as there's at least one electron. And I'm going to put that, at least one electron. This guy has 2, that's perfectly fine. This is considered the HOMO of ground state. In that ground state, that HOMO has 2 electrons. LUMO, remember we said always has 0 because it's the lowest unoccupied. If I'm going upwards now, 1 has, so it's occupied, 2 does have electrons, 3 doesn't, 4 doesn't, but 3 is lower than 4, therefore 3 becomes LUMO. He's the lowest with the unoccupied. 2 is lower, yes, but it has electrons, therefore it can't be considered LUMO. LUMO, yes.